In the last video, we talked about using calorimetry to calculate enthalpy changes. In this one, I want to cover Hess's Law. So remember, we're going to look at a few different ways to calculate the enthalpy change. Remember, the enthalpy of our reaction is the heat of our reaction. So when we say enthalpy change is our system, our reaction gaining heat energy or losing heat energy. And we did calorimetry, we're going to use Hess's Law in this video, then we're going to use standard heats of formation, and then bond dissociation energy. So those will be the four ways that we can calculate whether or not our system is gaining or losing heat energy. So Hess's Law. And Hess's Law is based on the fact that most chemical reactions don't actually occur in one step. So when we write reactants going to products, what we're generally writing is our net equation. Sometimes that actually goes through several steps before we get to that equation. And what Hess's Law says is that if we know the enthalpy change for each of the steps that sum together to produce the net, we can then add together those individual enthalpy changes to get the total. So the overall enthalpy change for a reaction is equal to the sum of the enthalpy changes for the individual steps in the reaction. So again, basically not all reactions take place in one step. We generally show just the net equation, but we're not always showing the steps that are occurring to get that net equation. So an example for us, the formation of ammonia actually takes place in two steps. So our first step, I have 2 hydrogen gas and that's reacting with 1 nitrogen gas to produce N2H4 gas. And then the enthalpy change for that step, so delta H, it is at standard state, so I'm going to put that not symbol and then a 1 because this is the first step of my reaction. And the enthalpy change for that step is 95.4 kilojoules per mole. And then the second step, the formation of ammonia, I have N2H4, and that's a gas. That's reacting with hydrogen to produce 2 ammonia. And my enthalpy change for that reaction, again at standard state, a subscript 2 because it's my second step, is 187.6 kilojoules per mole. So what we're going to do is we're going to write the net equation, and then we're also going to determine the overall enthalpy change for my reaction. So to write the net equation, I treat this as like you're adding 2 algebraic equations where the equal sign is the arrow, and then everything that's on my reactant side we're going to add together, everything that's on the product side we're going to add together, and then anything that's on both the reactant and the product side actually gets canceled out. So if I look at this, I have N2H4 on both sides, so we're actually going to cancel that out of my reaction when I add them together. And then here I have 2 hydrogen, here I have another hydrogen, so that's going to sum to 3 moles or molecules of hydrogen. So 3 hydrogen, and then everything on the product side needs to be on the product side, so I also have an N2. And then the only thing I have on my reactant side, 2 ammonia. And then always double check to make sure that that balances, to make sure you didn't miss anything. So 3 H2s give me 6 hydrogen atoms. 2 ammonia, right, 2 times 3 gives me 6 hydrogen atoms. Diatomic nitrogen to 2 nitrogen atoms, and then 2 ammonia gives me 2 nitrogen atoms. So it does balance. So that would be my net equation. To figure out my overall enthalpy change for this reaction, you just then add together the enthalpy changes for the individual steps in the reaction. So I'm going to take a 95.4 kilojoules per mole, and then I'm going to add to that a negative 187.6 kilojoules per mole. And then just be careful, I'm adding a negative value, so don't mess up your signs. And I end up that the enthalpy change for this reaction is a negative 92.2 kilojoules per mole. And then is that exothermic or endothermic? Yeah, good, exothermic, right? My sign is a negative value, right? I have a negative delta H, so that means that my final is less than my initial, so it lost heat energy. By it, I mean my reaction, right? My surroundings then gained heat energy. Specifically, they gained 92.2 kilojoules per mole, right? Energy is conserved. Another example for us, and this one's going to be slightly different. In this one, I'm actually going to give us the net equation, and then I'm going to give you the steps, and we're going to need to manipulate the steps so that they match the net equation. So this one's for methane combustion, and our net, this is kind of our goal. This is when we add them together, what we want it to look like. So I'm going to have carbon and 4 hydrogens, so methane. We would have learned to name it as carbon tetrahydride. And then I'm adding 2 oxygen gases. Remember, combustion is always adding oxygen, and then carbon dioxide is always one of our products. This is also a gas. And then we're also getting water, which is a liquid at the temperature that this reaction is being run at. The water could actually be gas or liquid. In this one, it's liquid. And then the steps that make it up, we actually have 2 individual steps. My first one, I have methane plus oxygen gas. That methane's a gas also, sorry. Going to CH2O plus water gas. And then in my next step, I have CH2 gas plus another oxygen gas, and then that's going to carbon dioxide plus water gas. I wrote this, sorry guys, I wrote this one wrong. It was water gas. And it's 3 steps, not 2, sorry. I keep on goofing this one up. I have water liquid going to water gas. And then we are given the enthalpy changes for these. So my enthalpy change for my first one, and I'm just gonna, I won't have room if I do delta H naught with a 1, a 2, and a 3, an equal sign for all of them, so I'm just gonna write the numbers. But these are the corresponding. So this is my enthalpy change for the first one, negative 284 kilojoules per mole. So delta H1. And then the enthalpy change for my second one, a negative 518 kilojoules per mole. And then my third one, 44.0. Try to write that a little neater for you, 44.0 kilojoules per mole. So the deal with this one, if I was to just add these straight together, they actually don't add up to my net. So they have to match this when I add them together, and they currently wouldn't. My CH2Os would cancel, those would go away. I would have, on my reactant side, I would have water gas, sorry, carbon, methane gas, CH4. I would have 2 oxygen because I would add those together, but I would also have a water liquid, and if I look at my net, there's no water liquid over there. And then on my product side, I would have carbon dioxide and 3 water gases, and if I look, I don't have any water that are in a gas form, but I do have 2 water liquids. So I know that I can't just straight add these up. And what we can do with the equations is we can manipulate them really however we want. I mean, I can't change subscripts and I can't remove things, but I can multiply them by 2, I can multiply them by 1/2, I can multiply them by 67.4, not that I would ever do that. But I can multiply them by something, I can divide them by something. The other thing I can do is I can reverse them. I can make my reactants products and my products reactants. The deal is though, whatever you do to the equation, you have to do to the corresponding enthalpy change. So if I was to take a reaction and multiply it by 2, then I have to take its enthalpy change and also multiply it by 2. Remember that my enthalpy change is per mole, and if I go and change the number of moles in my reaction by multiplying by 2, then I need to do the same thing to that enthalpy change. If I reverse a reaction, right, make my reactants products, my products reactants, then I have to change the sign, right? If it's endothermic in one direction, then it's going to be exothermic in the opposite direction. So whatever we do to our equation, we also have to do to the corresponding enthalpy change. So then my question is, what do I need to do to these equations to make them cancel, right? I need them to add up to the net, the one that I have highlighted in yellow, right? I know right now that I can just cancel these guys straight out, right? Those are going to cancel. And I want them to cancel because they're not part of my reaction. The other thing I would do before I start looking at reversing things, I try to look at the things that I don't want to change. So I know methane is a reactant, and of my 3 steps, the only one that has methane in is the first one, and it's already a reactant. So I don't want to reverse that. If I reversed it, then it would be on the wrong side. I also don't want to multiply it by anything because I have 1 methane in my net, and I have 1 methane here. If I multiplied it by something, I would have too many methanes. I'm going to look at reaction number 2. That one has carbon dioxide in it. Of all of my reaction steps, it's the only one that has carbon dioxide. It's already on the product side. I want it on the product side. There's 1 of them. I want 1 of them. So I know I'm also not going to do anything to that equation. So that step, nothing needs to happen to it. This last one, however, what I need to do is I'm going to reverse it, and I'm going to multiply it by 2. So I'm going to reverse and multiply it by 2. So when I do that, I'm actually going to have 2 water gases on my reactant side, right? I'm switching the reactants to the products, and then I'm going to have 2 water liquid on my product side, right? I reversed it, so reactants are products are reactants, and then I multiplied it by 2, so I have 2 moles in front of it. So this one I'm not going to really consider anymore because I changed it, which means I need to reverse, right? Whatever we do to the equation, right, the reaction step, I need to also do to my enthalpy change. So n multiply it by 2. So this is actually going to become a negative, right, because it was positive, 88.0 kilojoules per mole. Right? I multiply by 2, so 44 becomes 88. It was positive because I reversed it. I need to reverse the sign, and it's going to become negative. When I add these together now, I'm going to pick a totally different color here. When I add them together, they should match now. So these guys canceled, right? And now these 2 water gases, they're on the product side, will actually cancel those 2 water gases that are on my reactant side. So now when I add it together, I have methane, I have 2 oxygen, and that's all I have on my reactant side. So if I go up and look at my net, I have methane and 2 oxygen. On my product side, I have carbon dioxide, and I have 2 water liquid. Here I have carbon dioxide and 2 water liquid. So by taking my last reaction step, reversing it, multiplying it by 2, when I add them together, they now match the net equation. Again, I need to do that to my enthalpy change, however. So now when I determine my total, I'm going to add those together. So Hess's law says I can just simply add them together. So I'm going to have a negative 284 kilojoules per mole. I'm going to add to that a negative 518 kilojoules per mole. And then I'm going to add to that a negative 88.0 kilojoules per mole, right? Not the positive 44, right? Because that's not for a reaction that I used, right? What I did is I reversed it and multiplied it by 2. So that number right there, I reversed it by adding the negative sign and then multiplied it by 2 to get 88. So that's the one I want to add together. So grab my calculator. So negative 284, watch the signs again when you're doing this. And I end up with a negative 890 kilojoules per mole. Because I'm adding and subtracting, we're just using digits after the decimal point for our significant digits. So this had nothing after the decimal point, nothing after the decimal point, and 1 after the decimal point, so I want nothing after my decimal point. So we'll do one more example. This one's a little trickier. So again, I'm going to give us the net, and then I'm going to give us the steps, and then we're going to have to figure out how we need to manipulate them to get them to add up to our net equation. So this net is my goal. This is what we want it to look like. So I have iron 2 oxide plus carbon monoxide going to iron solid plus carbon dioxide. So that's my goal. And then my 3 equations, right? I have 3 iron, 3 oxide, and then I'm going to react to that with that carbon monoxide, and we're going to get 2 Fe3O4 plus, that's a 4, plus carbon dioxide. And my enthalpy change for this one, we'll just make a list again, is a negative 47.0 kilojoules per mole. We'll just put the units up here. My next one, Fe2O3, I'm reacting it with 3 carbon monoxides, and we're getting 2 iron plus 3 carbon dioxide. And my enthalpy change for this, a negative 25.0. And then my third reaction step, Fe3O4 plus another carbon monoxide going to 3 FeO plus carbon dioxide. And then my enthalpy change for my third reaction step is a positive 19.0 kilojoules per mole. So same sort of idea. What we need to do is we need to figure out how to rearrange these guys so that they match this net, right? The one I'm highlighting here is our goal. And then whatever we do to an individual step, we need to also do to its corresponding enthalpy change, right? If we reverse it, then the sign on our reaction is different. If you multiply it by some number, then we need to also multiply it. If you divide, which is a possibility, you need to divide it by that number. So I kind of do this the same way I was explaining before. So I'm gonna look for things that I know I don't want to change or things that I know that I need to change. So like my middle reaction here, it's the only one that just has plain iron solid. Sorry, I didn't give you the states on here, but it is solid. The only one that has iron solid in it. And I need that to be on the product side, and it is on the product side. So I know I don't want to reverse that reaction. Kind of my thought process is I'm just thinking, okay, what don't I want to do for sure? And then like, what do I know I want to do for sure? The only one of the reactions that I have that has iron 2 oxide in it is my last one. This is on the product side. I want it on the reactant side, so I know I need to reverse this one. So I know that has to happen. If I do that, then my F3O4 actually ends up on my product side. And if I go back up and look at this first one, it's already on the product side, and I don't want that as part of my net, so I know that that's going to have to cancel. So I know that for that to cancel, I'm going to have to reverse that one also, So I also need to reverse my first one. So I'm going to rewrite those three, just making those changes first, and then we can make additional changes if we need to. So my first one, I'm going to reverse it. So 2Fe3O4 plus carbon dioxide going to 3Fe2O3 plus carbon monoxide. And then I am going to just reverse the sign on my enthalpy change also. The second one I'm not going to do anything with right now, so I'm just going to keep it the same, Fe2O3 plus 3 carbon monoxide going to 2 iron plus 3 carbon dioxide. I didn't do anything to it, so I'm just writing down my enthalpy change just as it was. My last one, I am going to reverse it, so 3 FeOs plus carbon dioxide going to Fe3O4 plus carbon monoxide, and then because I reversed it, I'm going to put a negative in front of its enthalpy change, right? It was a positive 19, it's now a negative 19. So from here we can do this a couple different ways. If I look at some of the things right now, I have 3 iron oxide, and I know I only want 1, right? If I look at iron on my product side, right now I have 2 and I only want 1. So I actually need less than what I currently have, and I don't have a corresponding component on the other side to cancel those out. So I know that I can't make them less unless I divide by something. So what you can start doing, and I'm not going to do it this way, is I could take the bottom reaction, divide everything by 3 to get the 1 iron 2 oxide. I could take my my middle equation, divide everything by 2 to get the 1 iron, and then hopefully add it up. And that's probably quicker than how I'm going to do it. But for some reason, this way works better for me. If you like doing it that way, by all means, give it a shot. As usual, you don't have to do things my way. But what I'm going to do is I'm going to end up multiplying by numbers to get things to cancel. And then at the end, I'm actually going to have to reduce my equation. When I reduce it, I'm going to have to divide. So I'm going to multiply and then divide, which might seem silly. But for me, it's easier and it makes sense to me. If you don't like doing it this way, by all means, do it your own way. So how I'm going to do it is I know I need my Fe3O4s to cancel, and I know my Fe2s, O3s also need to cancel. Because if I go look at my net, I don't have them. So if I look at my second equation, I have 1 Fe2O3. If I look at my first equation, I have 3 of them. So what I'm going to do is I'm going to multiply everything in this second equation by 3, which means I also need to multiply my corresponding enthalpy change by 3. So this is going to become a 3. 3 times 3 is 9, so let's actually just change that to a 9. 2 times 3 is 6, so that's going to become a 6. And then 3 times 3 is 9, so that becomes a 9. I know that my Fe2s, O3s are now going to cancel. The next one I'm going to look at, my Fe3O4. On my first reaction, there's 2 of them. On my product side of my third reaction, my Fe3O4, there's only 1 of them. Again, to get them to cancel, they need to be the same number. So I'm going to take that bottom reaction, and I'm actually going to multiply the entire thing by 2. So I also need to multiply its enthalpy change by 2. So going through this 3, I'm going to multiply it by 2, so it becomes a 6. CO2, I'm multiplying the 1 by 2, so I'll put a 2 in front of it. This gets a 2, and then this also gets a 2, right? Everything is getting multiplied through by 2. Now I'm going to add them together. So I know that these ones will cancel, so that cancels with that one. I know that this cancels with this one, which is what I needed to happen, right? Neither one of those are part of my net equation, so they need to go away. I'm now going to add everything together and just kind of see what I have. So If I look at the number of carbon dioxides I have here, I have 3 of them. Here I have 9. So those 3 will cancel 3 on the other side, and that 9 will become a 6. If I look at my, let's take a different color. If I look at my carbon monoxides, I have 9 here. On this side, I have 3, right? 1 here. Sorry, 2 there, 1 here, so 3 total. So those ones will cancel 3 of those, so that becomes a 6. This is getting kind of messy, but let's just rewrite everything that's left. So what's not canceled is I have 6 iron 2 oxides. I have 6 carbon monoxides. I have 6 iron, plus I have 6 CO2s. So because I added those together, I am going to add these together. Remember that I'm not just adding a negative 25, I'm actually multiplying it by 3. So 3 times a negative 25 is a negative 75. So that's the number I'm going to add to it. So positive 47 plus a negative 75, and then plus 2 times a negative 19, so a negative 38. And I end up with a negative 66.0 kilojoules per mole. So we're almost there. This is where I said I was going to multiply and then divide. Because I have a 6 in front of all of these, I need to reduce it, right? If I divide them all by 6, then I get 1s, which is what I'm looking for. So divide everything through by 6. I need to divide this by 6. So FeO plus CO going to Fe plus my carbon dioxide. And then negative 66 divided by 6 gives me a negative 11.0 kilojoules per mole. And again, you might find this one easier to actually divide first instead of multiplying and then dividing, but you end up with fractions when you do that, and then you have to add fractions together, and then not everyone's great with that. For me, this is just easier to multiply them to get them to cancel and then just divide at the end.